In this talk, we present Feather, hierarchical querying for the edge. This project is a collaboration between me, Syed Hossein Mortazavi, and Muhammad Saleh, Moshe Gable, and Eyal Delara from the University of Toronto. Consider a hypothetical industrial IoT application deployed over a three-tier network. Machines and sensors on the factory floor generate large volumes of data used locally for latency process control decisions on the production line. Data in this setting is periodically forwarded to a local aggregation center covering one or a group of factories where more resource-intensive predictive maintenance models can be applied, and where latency requirements are less stringent. Finally, data is forwarded from the core to a cloud server, where management backend shows a web dashboard with global production status and inventory. It can also be used for training machine learning on historical data since more resources are available in the cloud. In a hierarchical environment, each regional office can be connected to multiple factory floors, and the cloud can be connected to multiple regional offices. The links between the edge and the regional offices have limited bandwidth, while the links between the regional office and the cloud have higher latencies. Now suppose that for the dashboard on the cloud, you want to run a distributed query that shows the maximum temperature for each type of machine in factory floors in the last 10 minutes. Querying geo-distributed databases traditionally falls into three general approaches. 1. Sending everything to the cloud and querying locally on the cloud. 2. Stream processing, which is only suitable for continuous queries and has high deployment overhead. And 3. Querying edge data centers and aggregating the results on the cloud node. Alternatively, we propose Feather, a hybrid approach that exploits the hierarchical structure of an eventually consistent geo-distributed database and takes benefit of data that has been pushed to intermediate nodes to trade temporal accuracy or freshness for improved latency and reduced bandwidth. Feather supports on-demand queries with user-specified freshness guarantees. By carefully keeping track of update times for data stored at intermediate nodes, Feather avoids querying remote edges, allowing for faster responses and conserving bandwidth. Feather queries include a freshness constraint provided by users which we call laxity. This constraint guarantees that only data created up to a certain time t requested by the user will be in the result set. Effectively, we are relaxing the freshness requirements on the data. The main contributions of this project can be summarized as follows. 1. Feather provides global querying over a hierarchical geo-distributed database by giving users control over staleness and query latency requirements. And 2. Feather provides fault tolerance with estimates about result completeness and coverage. In Feather, the user specifies the data freshness criteria and the system tries to minimize data transfer and query response time by not visiting nodes that we know have already pushed or replicated their data to the parent node. By tuning the laxity constraint, system operators can fine-tune the trade-off between query response time and freshness. Higher laxity thresholds can result in faster response latency and reduced bandwidth at the cost of more stale data. On the other hand, to achieve fresh results, more bandwidth may be used and the response latency will be higher. Freshness guarantee is similar to formal treatments such as delta atomicity and T-freshness. To better understand Feather's functionality, we present the following example which describes a series of events in a geo-distributed setting. This example includes 3 factories, 2 regional aggregation offices, and a cloud node. We assume that rows K1 to K7 are written to factory edge nodes A, B, and C between times 0 and 8. For example, K1 is written to factory C at time 2 and K2 is written to factory A at time 3. Also, every 3 time units, dirty data on a factory is pushed to the parent node. For instance, K2 is pushed onto regional office D at time 4. This process continues until time 8, when we run a query on the cloud node looking for the average values of k with a latency of 2. This means that our system should at least include k1, k2, k3, and k7 in the result set to satisfy the latency guarantee, as these values were created before time 6. However, values k1, k2, and k3 can be retrieved from regional office E and D. The query starts from the cloud and then is sent to the two regional offices. Because factory A and C had pushed their data to their parents at times 6 and 7, the query does not need to further run on factory A and C, as the parent nodes are certain that they have all data from A and C up to time 6. But accessing factory B is necessary to ensure values created after the last time factory B pushed its data is included. The results are then aggregated as we traverse the tree back up and a single value is passed on to each parent. Note that K5 is also included in the result set, although it was created after time 6. Feather supports almost all features available in high-performance tabular data stores, namely filtering, aggregation, grouping, ordering, and limiting of the result set. As these operations are done on intermediate nodes, data transfer is minimized. All Feather queries come with coverage estimation that determines what percentage of the nodes were traversed and estimates how many roads were not accessed because of the freshness laxity. When a node or link goes down, a branch may become inaccessible. In this case, Feather either relaxes the freshness guarantee and provides best results that are not as fresh, or returns partial results that are up to date. In both cases, the failure is communicated to the user. The answer includes a subtree that was excluded, as well as the estimated number of roads that the query is missing, using the coverage feature. We test the performance of Feather by using 1 month of data generated from the NYC taxi dataset, where each taxi ride drop-off zone is mapped to the nearest edge node. We test Feather on 3 different topologies. The Y topology with a depth of 3, where each non-leaf node has 10 children, a medium topology with a depth of 4, where each non-leaf node has 3 children, and a deep topology with a depth of 5, where again each non-leaf node has 3 children. We use 3 types of queries to test Feather: select all, group by, and aggregate queries. Feather is designed to provide control trade-off of answer latency and answer staleness in global queries. This trade-off depends on query laxity, network topology, period of the push time, and data update distribution among the edges. To evaluate this trade-off, we run controlled experiments where we vary the first 3 while fixing the data distribution to the NYC taxi data. We compare Feather's hybrid approach to the 2 prevailing methods in geo-distributed databases: querying the cloud replica and querying the edge nodes. This slide shows the performance of global queries for the medium topology for several latency levels. When queries are executed on the cloud, the results are more stale, but the query response latency is lower. Sending all queries to the edge with a latency of 0 results in fresh answer, but high latency and high data usage. Feather Freshness Guarantee, or hybrid, provides flexible trade-off of latency, bandwidth, and staleness while guaranteeing the freshness threshold L. So how can a system operator choose the right staleness or latency values? This is achieved by plotting the latency-staleness trade-off curve. Using this curve, a system operator can choose the latency that will be achieved based on a selected staleness. In this figure, each point depicts the answer staleness and latency for that query. and the color indicates the lowest tier involved in answering the query. The most immediate observation is that query performance is clustered based on the depth of the lowest tier involved in answering them. This is partly because our control topologies are similar latencies for all nodes in a tier, and the key factor is the round-trip time from cloud to the most distant node. As mentioned before, in Feather, each global query returns an estimate of the number of rows involved in the answer. We see a strong agreement between the real and the estimated row coverage as presented in the figure. The mean coverage error is only 2.7%, confirming the accuracy of the estimator. When more nodes are involved in answering a query, the estimate tends to be more accurate. We also test Feather over a real edge network consisting of 10 data centers from 3 different cloud operators spread over 3 continents. The figure shows the topology of the edge network and the mean round-trip latency between every 2 data centers. We use geo-tagged public tweets as a dataset for this experiment to simulate the pattern of event arrivals. We scraped a total of 1 million tweets over a 1-week period from December 2019. For this experiment, we do not add any artificial network delay or jitter. The left figure shows the latency staleness trade-off for queries in a Twitter experiment. While the overall shape of the curve remains similar to those seen in the controlled experiment, we observe many more clusters. Although the depth of the lower tier still determines query performance, we observe that the key factor is a round-trip time from the cloud to the most distant node that participated in answering the query. Since the link latency in this experiment is much more varied, we can observe more clusters and even associate some of them with specific nodes. Finally, the figure in the right confirms that coverage estimation remains very accurate in a real-world experiment, with a mean error of only 0.4%. You can read our paper for additional results, such as the number of rows sent by each type of query, average number of rows accessed by each local edge replica as a function of laxity, 95th percentile of latency as a function of laxity for different push periods, and the mean latency and average work per edge as a function of laxity. In this work, we presented Feather, a geo-distributed, hierarchical, eventually consistent tabular data store that supports efficient global queries. Feather provides a user-controlled trade-off between latency, staleness, bandwidth, and load on edge nodes, and it provides completeness and coverage estimates on the result sets. As for future work, we plan to extend Feather in 2 directions. First, we want to support more types of applications by allowing data to flow downstream on demand and improve the implementation for non-disjoint keys. Second, we want to investigate dynamic control policies for the latency staleness trade-off. By tuning the laxity parameter dynamically, we can better adapt to changes in data distribution and query patterns.